All right, we're going to look at section 5.3, which is on the fundamental theorem of calculus. There are two parts to the fundamental theorem, and we're going to start with part one. But before we get into all this, I'm gonna slide down here and sort of give away the punchline. The main thing that this fundamental theorem part one says is that the processes of integration and differentiation undo each other. So they are like inverse processes. So what we're going to do is we're going to look at this graph here, and we're going to kind of work a derivative out of it and show how derivatives and definite integrals are related to each other. So first up, what I've got here, this is the t-axis. This is some function y equals f of t. Now, I'm letting x be a variable that's right here, and a is this over here. So this integral right here gives us this area. And I'm making my f, my capital F, be this function that tells us the area starting here and going up to x. So all this. And the idea here is if this were an animation, I could move this x, I could move it back and forth and get, larger areas and or smaller areas by sliding it back here and only getting this. But the idea is this capital F tells us the area starting at A and going out to x. So f of x gives the area under the curve from A to x. So what I want to do now is I want to look at a thin slice of this right over here at x. And I'm going to, on this diagram, I'm going to draw in my A. I left it off because it's not, we don't necessarily need it, but I do want to talk about it a little bit. So I want to look at finding the area of the slice. All right, so to find the area of the slice, one way we could do that is by saying, well, it's if I computed the area from, if I did the area from A up to x plus h, and then I also computed the area from A up to x, that would give me this right here. This is the area up to x plus h. This is the area up to x. So this gives me the area of the slice, just by subtracting those two, and it just leaves the slice. Now, that's approximately equal to this. What is this? Well, f of x, that's the height of the slice, at least on this side. And h is the width of the slice. So if I take f of x times h, that's approximately the area of that slice. Now, it's approximate because if you come in here and you look at it really closely, on one side, it's slightly higher than the other side. So that's not exactly the area. It's going to be counting, there's going to be a little bit of error. But that's approximately correct. And if you take this and rearrange it, let me erase some of this stuff. If you take this and rearrange it, basically divide by h, this area, or this f of x is approximately f of x plus h minus f of x over h. And that looks a lot like the derivative. So as h goes to 0, the approximation becomes exact. And so what we get is this little f is equal to the limit as h goes to 0 of big F of x plus h minus big F of x over h. This is the derivative. So what this says is this side over here is f of x, and on the other side what we have is big F prime of x. So that shows us that the derivative is related to this. And we can write this out by saying, essentially what this says is the derivative is the inverse process of the derivative. We can write it out like this and say if f is continuous on the interval from a to b, then this function f of x that we get from this is also continuous, and little f is the derivative of big F. So anyway, that's sort of a derivation of this part of the fundamental theorem. And the important thing to know is how to apply this right here. Now, applying this is actually a lot easier than the derivation. And it can be written more compactly using the Leibniz notation that says if you take the derivative of this integral of f of t, what you get is f of x. So in other words, what's happening here with this function f, you're integrating it, or rather, yeah, you're integrating it, then you're taking its derivative, and it gives you back f. So there's really not much at all to do on these problems. This right here says, find the derivative of this function. Well, the derivative of this function, it's the integral of that. So the answer to this is f prime of x is just x squared plus 1. This next one, find the derivative of this function. F of z equals integral from 4 to z of t to the 4th dt. So the integral and the derivative undo each other. F prime of z is going to be just z to the 4th. And notice that other endpoint doesn't really do anything. Up here we had a 0, down here we had a 4. It doesn't matter. You wind up just plugging in the upper endpoint for the variable, and that's all there is to it. Let's see, this one down here. This one is trying to be slightly tricky by saying find the derivative of this function. Notice they've got the constant on top and they've got the x on bottom. So all you have to do for this is rewrite it. Put the constant on bottom, the variable on top. Of course, when you swap those, it changes the sign. So you've got to slap a negative on the front. So the derivative of this is f prime of t is just negative sine x plus cosine x. And you can distribute that through if you want to. In this last example, again, there's nothing to it. We're taking the derivative of the integral of this thing. There's actually a typo here. This should be a t, not an x. So this is just going to give us e to the sine x. All right, so these examples might be a little bit silly, but the important thing is integration and derivatives, integration and differentiation are inverse processes of each other.